Right, let's get this underway. Share my screen. So, good morning, everybody. My name's Sean Manzi, and I'm a colleague of Dan's in the Pencord team. And I've been with Pencord about 6 years now, 6 years or so. I know you lose track of these things quite easily. But so one of my specialisms is working with a technique called network analysis. And today I'm going to introduce to you the concepts around the network analysis, and we'll look at how it can be applied to healthcare data in a very light and easy way. Then there are two following optional sessions, which I believe are in December, on advanced network analysis, where we'll go into more depth, looking at actual network analytics and network metrics, and also looking at more complex network visualizations. But today it's going to be more of a easy introduction, so nothing too stressful. So the outline for the session today is we're going to look at what network analysis is and how it's used in different areas. Then go on to look at the components that make up a network. Then go more into actually how we do network analysis and looking at transforming data for network analysis. Then at the towards the end, we're going to actually build a network graph from the data that we create. So that's the overview of what we'll be doing today. And so kind of what we're trying to get to today is really understanding what are these network graphs and how are they put together, because that's kind of the key difficulty with them, really, is actually working out how to transform your data into something that you're able to create a network from. And then being able to undertake that transformation, and then also then turning that into a network graph itself. And we'll be using the Python library NetworkX to do that. So network analysis and its uses. What is a network? So networks came about in actually trying to look at originally the it was the bridges of I can never say it, Kunungageseg, I believe. It's something like that. But this is essentially a traveling salesman problem, where you're trying to cross bridges and work out how to cross each bridge only once. And what they were trying to do is work out the best way to walk around these gardens. And they had a series of bridges, and Euler came up with this way to be able to, he used network graphs and graph theory to actually be able to map the shortest path across these bridges without only crossing the same bridge once. And in this way, graph theory and use of networks has grown, and it's been used to study the function of large and complex systems. What they're very useful for is taking lots of complex data in a system that you're not sure what it looks like, and honing that down to visualize all the relationships and interactions between the components of the system in what is a more understandable and relatable way. And so it's been able to take these kind of abstract systems and represent them in a way that's easy for us to understand and to communicate. So networks often get used, they're used all across various different areas. So they're quite commonly used for airline logistics and mapping out the movement of aircraft across the globe. They are used in working out how banking transactions are linked up across the world. Social networks is kind of one of the key modern applications of network analysis, and all of your friend requests, your friend suggestions on Facebook and Instagram and such, they are the result of a network analysis in the background, looking at who you are most closely linked to, but not actually linked to yet, and making suggestions based on that proximity of you to other people. So if you use any social networks, then you will be a part of a network analysis being run by Facebook and such. More recently, looking at healthcare. So here the example of links between physicians and patients. And this is the type of network that we'll be looking to try and create, looking at the links between services and how patients are using those services. And then supply chains, again, kind of the logistics side of things, and people, how trucks are moving between warehouses, and within that you can embed a lot of information about the capacity of the trucks, or how far they're traveling, and looking at how much material is being moved to a particular warehouse. So these are all big, complex systems, and it's the network, this network representation of the data that makes it user-friendly and easy to understand. So here's an example from the aviation industry of flight routes in the United States, and looking at, we've got the large airports represented here in red, and the smaller airports represented in blue. And the routes, the links between, are these green lines that are linking the different airports together. And one thing you'll notice here is that the dots, the airports themselves, are of different sizes. And this is just one way in which we can embed different pieces of information within a network to start making it more useful. Here, this is representing the number of ingoing and outgoing flights. So it's a network metric that's called degree. And the size of the node here is determined by those numbers of flights. And so we can see what are the busiest airports, what are the biggest ones. Here, it's you've got Atlanta and Denver being major transportation hubs, and you can see that in the data. Here's an example of, this is some Twitter data that has been turned into a network graph. And here, this is looking at different keywords that are used within Twitter and the links between them. and where they're used in conjunction. And in this way, we can start creating knowledge maps about what's being talked about in social media. And again, noting the different sizes of the dots or the nodes, which are the keywords themselves, and the links between them. And here you can actually start to see the different sizes of the links, which is where they're being weighted. So the amount of activity that is going on between two nodes can be represented as the thickness of the line or the edge linking those two nodes. Here actually is a really nice example of work that was done by last year's HSMA and PSMA cohorts. And this is a group from Devon and Cornwall police who were looking at the links between offenders and their victims and trying to understand how these different groups are linked and how you get this grouping of different offenders, groups around different groups of victims, and so that they can start thinking about interventions to help, one, support victims, but also to prevent future offending from the known regular offenders. And yeah, this was a really nice project that got some traction within Devon and Cornwall police. And the video of their final presentation, you might have seen if you're at the HSMA 3 showcase. Otherwise, I know the video is up online. It's worth having a little look, as it's a nice example of using network analysis to understand this very complex, in this instance, social interaction between individuals. Now, I've got two interactive examples for you to have a little look at. I'm just going to paste these. I'm just going to paste these links in the chat for you. It's just, there we are. Just get the chat up. So these are two interactive applications that I've constructed, and these one is to exemplify how we can look at network data over time. And so the Network of Thrones is somebody went through all of the books and all of the TV series and looked at all the character interactions within the Game of Thrones series and turned them into network data, which seems quite a laborious task, but I'm glad they did, because it allowed me to turn this into an app that you can actually explore this data and look at the changes across the seasons and who are the most relatively important characters in terms of their interaction with other interactions with other characters. The second app is a more academic application. This is still a work in progress at the moment, but what we're looking at here is a systematic review of systematic reviews. So this is where they're looking at papers for where they're looking at convalescent plasma treatment for COVID-19. And there was a whole rush of reviews looking at any papers, any research studies that have been done and published on around convalescent plasma treatment. And what the group who I built this for were trying to look at was the disconnect, where there was disconnect and overlap between the different reviews that were being done, and trying to understand how these reviews were different, because there is no single review which includes all of the papers on all of the research papers on convalescent plasma treatment for COVID-19. So it becomes quite an interesting situation that you've got quite poor quality research being done, and by visualizing the data in this way, we can see that disconnect between across all these different systematic reviews that are being done. So hopefully those have loaded up okay. They do take a minute to start because they're on a development server, and I'm not paying for that at the moment. So hopefully have a little look and a little explore. They are both interactive network graphs that you can look at. Let's just see if it starts up for me. So here is the Network of Thrones app, and here we can zoom in on the network itself and see the links between the different characters. Here we've got the 10 10 most central characters given by these different graph metrics. And these are all measures of the linkage, the importance of each node within the network as measured in slightly different ways. And there's small little descriptions of the kind of the meaning of these different metrics below each of these. And so we can see the different values for them. And then we can look at these metrics across the different seasons of the TV series and compare different characters as well. And we can look at the different seasons and the different seasons of data and how that progresses through. And also by clicking on the nodes themselves, we can see which characters they are and what their graph metric values are as well. And so in this particular one, we get this main central group of where all the story's happening, but then we also get these outliers here. And if anybody remembers Game of Thrones, this particular group up here, they're all up at the wall in the north, but they are linked into the main story as well. But only, and we can start to look at who's linked through who. So Jon is linked to Ned Stark. They're spoken about in the same scene. But we have a separate group over here. And at this point, this is where Daenerys is still over on the other side of the ocean, and they're a separate group with no link to the rest of the main story. So that's one example. And bring the Wilfred app up. And so here we see the different systematic reviews here are labeled. And if we click on one of these, we can see information about the systematic review and then all of the primary research studies that it was linked to, that were cited within that review. We also get a view down here of publication timeline. So when all these different, the year in which all these different publications were published. And then Sankey diagrams of which are quite fun. We can look at the links between different features that we want that are of interest. So here we're looking at the year of the study, the type of study that was done, and the systematic review that it's linked to. And so these apps, just out of interest, these apps are built using a package or a library called Dash, and that's developed by Plotly. And these Plotly graphs as well, that Plotly is really useful for interactive data visualization, so we can get hover data to pop up and interact with the graphs themselves. Okay. Hopefully everybody's had a chance to have a little look at those couple of different apps and a little explore of kind of what network graphs look like and how they can be used to create data with these by using network metrics, but we can also embed data within the nodes and the edges themselves. So how can this be used for healthcare circumstances? You know, when does this become important and relevant for healthcare? So one of the biggest things over the last 6 years that I keep getting asked by people is, we would like to see our whole system. We want to be able to model our whole system and look at it. That's a really difficult proposition, because quite often healthcare systems, healthcare trusts, and all the services that they operate are extremely numerous. They're huge and complex systems. And to go through and manually map out all of those different services and how they're interacting with all the other services is an incredibly difficult proposition. They actually tried to do this with down in South Devon, looking at just at mental health and all of the different services that were being provided in South Devon and who they were interacting with. They tried for 2 years to do this, and they still had an incomplete map of what the system looked like. And then when they came to put any data into it, they found there either wasn't the data there, or it was extremely difficult to link the data up and make it relevant to what was actually happening. So the way that I've conceived of this is to be able to transform patient data to be able to drive a data-driven whole system representation of a healthcare system. And in this way, we look at the graph itself as the service structure. So this is your system. It's a map of the system itself. The nodes, which are the dots here, are the services themselves. The edges, the links between the different nodes, are the movement of patients. This is when chronologically they're moving from using one service and then they begin using another service subsequent to that. The weight is the level of activity, the number of patients who are within the data that you're looking at and moving chronologically between those services. And then we can put different node attributes in as different operational measures or improvement measures. For example, we might be looking at things like just the number of patients, we might be looking at the number of patients on a waiting list, or the referral to treatment time, the length of stay within a service. And we can change the node size or the node coloring to be able to represent one or more of these pieces of information. And so as we kind of go through these few sessions on network analysis, we'll be building up to being able to get to the point where we can develop graphs like this and look at these for understanding how whole healthcare system operations are taking place. So to go on to a bit of more of the kind of theory around this, we'll look at the components of a network and what makes up a network. So a network graph, it is a graph-based representation of a system. This is where a network graph can be plotted on a Cartesian coordinate system, and the relationships between the nodes can be described mathematically. And it's based on a pairwise relationship between entities. Now that's just a very fancy way of saying it's this link, these edges between these nodes. That is a pairwise relationship. That it is just node A is linked to node B via edge number 1. And so what we're doing is we're quantitatively encoding the properties of this system within the network structure, which enables us to be able to go on and ask questions of the network itself and understand what's happening within it. So here we see kind of a conceptual idea of the components of a network. Now, I use the term node for the dots, the R entities. They're also called vertices, just to confuse you, but that term's used interchangeably. And I tend to find it easier. A lot of the software actually refers to them as nodes. But if you go the mathematical bent and read into graph theory, they use the term vertices. So here we see V1, V2, V3, V4, V5 are all our nodes here. These are our entities. The links between them are the edges, and those are what are making that graph representation possible. There are different types of graph that we can have. So you get unordered pairs of nodes. So this is where we make no distinction between the order V1 is linked to V2 and V2 is linked to V1. They both mean exactly the same thing. However, if direction does matter, as for example in healthcare, we're interested in how many people are going from, for example, from the emergency department going to orthopedics. But we're interested in those that are going from the emergency department to orthopedics, as we wouldn't necessarily expect anybody to be going from orthopedics to the emergency department. So that's when we have a bidirectional graph, referred to in Network X as a and a lot of the literature as a digraph. And that is where order of pairs of nodes matter. And that's important to understand, as we have to, if we're doing ordering of pairs of nodes, we have to define that in the data that we put into the graph. Then we get our edge weights, which are the line thicknesses. That's the amount of activity, or the amount of, it's something moving between the two nodes. And then, as I mentioned, the node attributes, we can link any amount of data that's linked to the nodes itself and embed that within the nodes. And that can be then visualized either by size or color. So just a little bit more terminology for you. We get things called parallel edges. If you ever hear the term parallel edge, this is what we see between nodes V4 and V5 here. This is what we tend to see in digraphs. So we have a link between V5 and V4, and V4 and V5. Then we get loops, which are where there's a node is linking back on itself. So here we see that an example of that with V5. And these loops you see are common when you get re-referrals into a service without somebody using a service in between. Then we get adjacent edges and adjacent nodes. So the edge between V1 and V2 is adjacent to the edge between V2 and V5. And likewise, adjacent nodes, node V1 is adjacent to node V2, just next to. All of this language is kind of a little bit by the by, but it's useful if you're reading around network analysis at all, that these are the terms that you'll see used because it comes from that very formal mathematical background, which I'm avoiding today because it all gets a little bit technical and just a bit faffy for actually when you want to use network analysis. You just have to have a bit of you just have to understand what the network is more conceptually without necessarily understanding the maths behind it. Okay, so getting a bit more onto this practical side of things and how we actually do network analysis in practice with some real world data. When we build a network graph, there's certain bits of information that we need to be able to describe the graph and create that visual representation. So we build up two lists of data. So we have to create what's called a node list. And this is a list of all of our individual nodes, all our individual entities, whatever they might be. They could be people, they could be healthcare services, they could be airports. And we need to attribute them a unique ID. And then we also need to give them a label, a human readable label that makes sense to us. And then we can attach any kind of, any number of attributes that we want to them as well. Then, in addition to this node list, we need to create an edge list as well. And the edge list consists of two key pieces of information: the source node and the target node. So this is where the edge is going from the source of it and to the target. And this source and target information is based on the ID of the nodes. And this is how the node and edge list are linked together, that the IDs are used to create the edge list. And we'll see, and we'll create examples of these. And again, we can attach any number of attributes to the edges, and the most common one is the weight of the edge itself. Okay. Now we're going to talk about data transformation, because it's if you have the data, it's very easy to create a network graph from it. However, creating the data for a network graph is probably the more tricky thing to do. So it's good to talk through this process, and it's a good way to explore kind of this data engineering side of things, data transformation, that you'll be doing so much of with Python. So the data transformation process itself, just to talk through this, and we'll go through this kind of a bit more step by step, is we start with the raw data. And for healthcare data, in healthcare circumstances and examples that I'll be using around that, we're looking at patient level data. And we'll look more specifically at what data that is in a minute. The next step that we need to do is make sure that we clean our data. I'm sure this is something that you all do a lot of, probably. So here, we give it a good clean, looking at category consistency, pulling out negative dates, erroneous white space, all that kind of naming consistency through the data. Then we order our data, first of all, by patient, because we want to be able to look at their chronological use of data. So we're then organizing it by date. So when using patient episode data in a network, we're first of all, we're ordering it all by the patient, and then by date of the services that they've used. Because from that, we can go through and we can create what's called an adjacency matrix. And I will show an example of this and explain a little bit more about this shortly, as it's much easier with a visual to explain that. But this is how we can start. We create an adjacency matrix to map out the how all the links between the different nodes. And it's from this adjacency matrix that we can create our edge list to be able to see what our source and target nodes are. And then we use the unique instances of from within of our services, of our entities, to create our node list. Okay, so I'm sure I don't have to tell you this, but just a little note on data cleaning. When we're undertaking data cleaning, some of the key things to look out for are particularly capitalization inconsistencies. If you're using names as IDs, they must be exactly the same. One thing that I tend to do when cleaning data is I remove all capitalization from text strings, and that just means that there can be no issues with capitalization, as that does crop up a lot in the data that we see. Spelling mistakes, always a difficult one. Always worth creating that unique list of your categories and going through and looking through at are there any replications? Has it been spelt wrong? Somebody's gone in manually and written something in. And that happens a lot. Erroneous white space. This can be leading, trailing, and multiple spaces. Again, when computers are reading text strings, they will get confused by that, and that will result in another unique value if there's any erroneous white space in there. Incorrect date entries is always a difficult one. Quite often we see referral and discharge dates being reversed, so always a good one to go through and check for those. And then looking at where your missing data is, and whether that is important in the analysis that you're trying to undertake, and whether those entries should be removed. So going through and ordering data. So I mentioned that when we're looking at patient level data, we want to be ordering it first by the patient and then by date. And in this way, you can iterate, you can go down your data and iterate over it in loops to be able to select specific information out of it. So here, and this is a snapshot of the data set that we'll be using for today's first task. And this is a kind of a made up version, or synthetic data. Well, it's not really synthetic data, it's a heavily anonymized data that is loosely based on some mental health data. And what we have here, we have a unique client ID in our first column. So this is how we're identifying our individuals. Then we get a referral date, so the date that they came into contact with the service. Then the discharge date. And you can see that we've got NAs in here. So this is where somebody is still in that service. And in terms of completing your network, the way that I handle these is that I use the date of the data extraction to fill that missing data in, so it brings you up to date, just for completeness, because we're always looking for completeness in our data columns. Then we've got our referral source in here if we did want to use that, but the important one here is the team or the ward that somebody is on. And these are all the different services, and these will essentially be our labels for our different nodes when we go through and create the network. So as you can see here, this data has been ordered first of all by patient and then by referral date. And this gives the patient history within this data extract of all the different services and the order in which they have accessed those services. And it doesn't matter if they're accessing more than one service at once, we're just looking at the order in which they've accessed those services. Now, I mentioned this term adjacency matrix. Now, An adjacency matrix is an example of what's called a sparse matrix. And a sparse matrix is one where you have entries for every possible combination within a two-dimensional matrix. And so more practically, we first create a matrix of zeros, which is n services by n services in size. And what I mean here is that its number of rows and number of columns is equal to the number of unique services that we have within our data, our number of unique entities that we want to use within our network. So for example here, say we have 100 different wards and teams, 100 different unique ones, then our adjacency matrix will be 100 rows by 100 columns. And then we can go through and we can iterate over our data here in order, going through and go, okay, the first person here, they accessed link center in area 1. Their next, what they did next was they accessed area 31 adult community sector service here. So we can go to our adjacency matrix, find that in the row, the first service that they accessed, then go along the columns and find the second service that they accessed. And then we add 1 in that cell. And that, in that way, we can build up this adjacency matrix, counting the number of instances where people have moved between one service and another, and that they are there. Those are the edges. Those are our links between our nodes. And this is how we build up this network, this network representation. And here you can see that there are between service 1 and service 2 here and service 1, there is 1 patient moving between them, whereas over here between number 5 and number 5, we've actually got 9 people moving between them. And yeah, 2 here between 6 and 5. So we're basically just going down and counting the movements between these different services. So what we then get is so this is how we're building our edge list, and we've got our sources in the rows and our target nodes in the column, and we've got the frequency count in the cell. So now let's look at an example of a node list. So here we see this is kind of the standard output that I tend to produce when creating a node list. And here I've got the required and the optional fields that columns that you need. So when creating a node list, the actual only required piece of information is an ID, as this is what you use to determine your source and targets for your edges. However, to make them meaningful, it is useful to have a label. then we can add different continuous and discrete attributes as we might want to. So here we can see the setting, or the kind of the general type of service here. So this one's these are out of area services at the top, and then we have community services here. And in this way, we can use these to color different nodes within our visualization to indicate and differentiate between particular services as we want by categorizing them. But then we can also give continuous data. So here we've got the mean length of stay and the median length of stay as well. And in this way, this is kind of, it's relatively straightforward. We've gone through a little bit of a process of creating our adjacency matrix. But our node list is actually just our unique services and any information we want to give about them. So the edge list then, here the required columns are a couple more. That we have the source, and that's the unique ID from our node list, and the target, again, from our node list. And these are picked out from the adjacency matrix where it is greater than 0, where a cell is greater than 0, we get this source target link given. And that is, so it is source and target are the two key pieces of information, but we also need to give our edges a unique ID as well. And so optionally, we can also give the type of edge that it is, but this is only required for Gephi. And this is a piece of software that we will look at for producing very nice network visualizations, but it's also difficult to get the replication of visualization in it. So there are certain instances when we do and don't use Gephi, but we'll cover that in the advanced sessions. And then we can add our attributes as well. And in this instance here, we've got the weight of so the amount of activity along that edge. Okay, right, that's enough for the moment, I think. We will take a quick break, and let me just have, what time is it? Right, so 10:30 now. We're going to have a quick break for 15 minutes, just kind of let that all digest and go in. And we'll reconvene at 11:15. I think, let me just double check that on my schedule. Yep, reconvene at 11:15, and we'll be doing some transformation of data into node lists and edge lists and creating your own. So enjoy a nice break, and I'll see you in 15 minutes. Thank you. Just restart the recording. And so I talked a lot during that first session there. I'm just going to open up the floor just for 5 minutes or so, and just see if there are any questions that came out of that first half.
I've just got one question, Sean, if that's all right. It's
Yes.
sort of a theoretical question related to network modeling. Do you need to have a complex network with lots of paths and weights to be able to model a system, as versus like a very simple, kind of linear model? I'm guessing graph theoretical tools will only work if you've got a larger system. Would that be the case with lots of nodes?
No,
so what I'm getting at is there like a minimum number of nodes or edges that you need for this to work?
No, you can do this with much smaller systems as well. And we actually did some work looking at just kind of individual patients and mapping their service use. So these were much smaller graphs with kind of maybe 10, 15 nodes. So yeah, it absolutely works in that way. It's just that it's kind of the questions that you might be asking might be a little bit different. So one of the big ones is looking at the change in service use over time in healthcare. And so you could actually split up individual patients or much simpler pathways and just look at how they change, their activity changes over time, and compare them from month to month, for example, or year to year. So absolutely works with much smaller data sets. They're much easier to visualize as well, which is nice.
Thanks.
Any other questions at all coming up? If you do think of anything, just pop it in the chat and we can always come back to it afterwards. But yeah, and you can always come back to me on Slack if you have questions thinking about anything later. This kind of, today's very much just an introduction to and trying to get the idea of some of the concepts around network analysis, as it's one of these techniques which is going to become, I think, more important in looking at healthcare operations over time, as finding it more and more useful. So it's good to get a grip on this technique now. Okay, well, now I think it's time to turn things over to yourselves. So let me introduce your first task. So what we're going to do now is you're going to transform some data. The task itself, so there's within the session materials that you've downloaded, there is I'll just bring it up. I get the correct one. So you should have a folder labeled task files, and within that you will have, sorry, I need to put it on that screen. You'll have a folder labeled task files, and within there there's a file called data transformation jumbled.py, and that's the one that we're going to use for this first task. There's also another folder in there called data, and within that we have the PD data HSMA 2020. This was used for last year's as well. And so that's the data that we're going to be using for this. And the task is, so this is within this PI file, this is an example of how to transform patient episode data ready for a network analysis. And kind of one of the reasons that do this one is that it actually gives you all of the required columns for use with multiple network analyses libraries. Today we're going to be using Network X, which is great for network analysis and some basic visualizations. But there's also some other libraries that we'll look at in the advanced session, which produce these kind of interactive diagrams and produce some nicer looking plots. So the big one here is what I've done is as you can tell by the name of the file, I have jumbled up the code into and this is split into 8 different blocks and all jumbled up. So your task is to rebuild the code and get it to work. I've put the package imports and the data read function in the correct position at the top. And so you just need to get these 8 blocks of code into the correct order and run the code successfully using that PD data HSMA set data set, and you will find that you get 3 different outputs. You'll get the adjacency matrix, you'll get the node list, and you'll get the edge list output. Now, an important one is to remember to set your working directory, and you'll want to set your working directory as the task file. Sorry, the task folder, as the read-in function for the data is set to the data folder, and it will dig down and pull the PD data HSMA 2020 CSV into this. So as you can see, this is the structure of the PI file, and you've got the different blocks which are all labeled up in the various bits that they do. And yeah, you just need to go through looking and remembering, hint, look at the back at the slides and the order in which we were doing the different tasks, and reorder these blocks of code. So I'm just going to stop sharing now and put you into your breakout rooms. Okay, so this is set up the same as Dan has done the previous sessions, and you can just choose to go into your different peer support groups. Okay. Great. Is everybody all okay here in the main room? Just let me know if you need assigning if you didn't get the invitation to join a group, and I can assign you. Or yeah, do just carry on if you're in this in the main room.
Anybody in here?
Morning.
Oh, hi.
Someone's awake.
Just one person. You're getting on okay?
Yeah, I think so. I've run into an error and I'm just trying to work out why that's come about.
I don't know if you're on your own in this room or not, but I wonder if it would be easier to share your screen and then people can dive in a bit.
Yeah. Let's do that. Okey-doke. Does that come up?
Yeah.
Okay. Yeah. So it's I think it looks so far like it's in the right order, but it might not be because it's throwing this.
In close to have a look. Hang on, let's see.
We've got this. It can't find the length of
Starting with the
stay.
two data cleanings. Replace missing dates with a date and starting. What's the first one?
So I got data cleaning.
I think they're the wrong way around, Ed.
Yeah, I think.
Right.
Yeah.
Yeah, that might be. Oh yeah, of course. Yep. Yeah, I might have to check that. I might have done that elsewhere as well. Put it where there's two.
Yeah.
Change.
Oops. I lost you. Line.
Plus. Now, I'm not sure if that's.
Just scroll down again. What do you have after the two data cleanings? Create the adjacency matrix here. I think that's probably correct. Yeah.
Create node list. Not sure what the output is meant to look like, because it's run without any errors, but I'm not sure if it's meant to have generated.
Yeah, he said there should be 3 lots of output, didn't he?
I think if you look in your folder, it will be in. They've created it in the folder.
Yeah,
brilliant.
I see. Yeah.
I was a bit lost in that as well.
One node list. The other one. There we go. Stop share.
Is that producing any output?
Yeah, I did. Yeah, I got it.
Oh, great.
Yeah.
Okay, great. We've got everybody coming back in now. Right, I think should be all the rooms closed and got everybody back. Okay. So how was that for everybody? Did all of the groups, well, did anybody not manage to get the code to run? No, that's brilliant. That's positive. This is it was great to see that yeah, you were doing the task, but actually everybody was going back through and trying to work out what the different, breaking it down a bit more and looking at what the different sections of code were actually doing and producing, because you know that's really the key here. As much as being able to write your own code, it's quite important to be able to read somebody else's code and to be able to unpick what's happening in it. There's kind of a few interesting techniques in there, kind of this creation when you're creating the adjacency matrix, and being able to create a sparse matrix and then iterate over it to populate that is a useful technique to learn. Working with time and date data, obviously an important one. Just learning to use those time delta functions is good to see. Is sometimes quite useful to see working examples of these. Off of the back of the task, were there any particular questions that came up? Oh, I see one here. No, so any questions coming from anybody at all? What was the answer? Okay, yep, I can show you what the answer is. Just making sure that I have opened the right file. Yeah. Okay, what I'll do is I'll go through and just unjumble it very quickly with you. Yeah, so Sam, the main thing was to be able to create those 3 output files. Those were what you were really after. The being able to get this node, the node and the edge list, because those are what we need to be able to create our network, and everything kind of follows on from that. This data transformation process is just kind of the key first step, but it takes more code to transform the data for a network than it does to analyze the network itself and create a visualization. Ironically, it's just that more complex process. But if you can learn to be able to create this kind of data for healthcare, in this healthcare instance, then it makes it easier to extrapolate and apply this to different situations and see what that kind of flow is of getting to being able to create a network yourselves. So just to run through the task quickly, we start with the first block of code that we need is the data cleaning. And there's two data cleaning blocks purposefully, just to make it a little bit more confusing. But it sounded like everybody got there correctly, that the first thing that you need to do is actually clean the data in terms of replacing missing values, removing rows with essential missing data. So where we're referring those without a, removing those without a referral date, because without a referral date, we don't know, we can't order that particular piece of information, that particular row of data chronologically. And as I heard a couple of people discussing, yep, you could go away and find that information potentially. Sometimes it just doesn't exist, it's just missing data. But yeah, it depends on how essential it is to go away and to find that missing data. So the second one then is the, as I think everybody got, is the second data cleaning block, where we're actually ordering the data. And here this is, so sorting, first of all, based on the client ID and then on the referral date. Here we're actually amalgamating all of the out of area, so anything from outside of the main geographic region into a single category. And this kind of amalgamation can be really useful, and this is kind of an example of how to do this with something called a mask. And being able to do this enables you to be able to change the resolution of your data. So you could actually simplify this and look at it, you could have more general categories for each type of team and amalgamate them into single entities. And that's, again, a useful technique for simplifying what you're looking at as you're asking different questions of the data. So once we cleaned our data, we then want to go in and create the adjacency matrix. Now, again, as picked up, there are two blocks here. And in the first, we are creating our empty adjacency matrix. So that's the kind of key first stage. So we're finding out how many unique teams, how many teams we have, and then using that number to create an empty matrix of zeros, and then getting our list of unique clients. The next step is then to iterate over our now cleaned and sorted data. And to go through working down client ID by client ID, extracting their data, looking at that, and going from one to the next. And looking at the next service on and creating those source and target links. And here you get the output of the serve move matrix, that sparse matrix. Next, then, as everybody rightly, I think rightly picked up, it doesn't actually matter whether you create the edge list or the node list first. It's just making sure that we get the node and edge creation in the right order. So for creating the edge list, this is where we go through, and again, we're iterating over the rows and the columns to be able to select those source and target, that source and target information. And then that is then concatenated with the term directed, and then it's all stacked up together, all of our source and target information, the edge type, some unique IDs, and the edge weights as well. And because of when it's stacked in a NumPy, using NumPy bstack, we need to transpose the data, just flip it round, and then we can add our column, turn it into a pandas data frame, and add our column names and output the edge list. Then we get the node list, and within this we are first of all getting the mean and median length of stay, then building up our data frame with a few different pieces of information first of all, so that we get the team name, and then encoding that as a categorical variable, and adding the setting as an additional attribute to it. Then we stack all this together and we get our ID, the label, mean length of stay, median length of stay, and setting as our output. So if I just run that quickly, we can then see that we get what are our outputs called? So we've got serve move that we can see here. So our sparse matrix, then get our edge list, which is values, edges df. And here we see our source, target, type, ID, and weight. And then we get nodes df. And we get our ID, label, mean, median length of stay, and the setting. And those should have all turned up in your data file when you've run this, and they've been output there. I'm in the wrong one. So you'll have edgelist.csv, nodelist.csv, and serve move matrix. And so this is quite a generic process for going through and creating this network data, and one that hopefully you can make use of if you decide to go forward and do some network analysis. That this base way of transforming your data, you can do this with any data that you might like to use once you identify what your entities are and what your edges are. Okay, so the next thing we're going to do, sorry, just I'll just pause there. Any questions coming out of that at all? Just have a look. Have we got? Does it matter if you calculate the nodes before edges? No, sorry. Yeah, not in this code here. Is there anything else at all? No? Okay. well, let's get on with building a network graph then. So, building a network graph. So, reasonably simple process. And these flow diagrams just show what the generic process is and then what the process is using the NetworkX library. So we start by reading in the data. And then we need to initialize an empty graph object. And this just means that it's like making an empty list in Python, that you go, here's my graph object, and it's ready to take some data. Then we format the node and edge data so that it is ready for NetworkX to be able, or the library that you're using to be able to read is in the correct format for that particular library. And then we add the nodes and the edges to the graph object. And then finally, we just plot it. Simple as that. So in NetworkX, this amounts to reading in our data, easiest way using pandas read CSV. And then we use the NetworkX graph function to create our empty graph. Then we need to create tuples. NetworkX takes its node and edge data in the form of tuples. So these are mutable objects that I'm sure Dan's been telling you about. And those tuples are made up of list and dictionary objects. And we'll look at that in more detail in a minute. Then we use the add nodes from and add edges from functions within NetworkX to add those node and edges to our graph object. And then we create a layout. So we create a position for all of our nodes. And there's a number of different algorithms that allow you to do this. And we'll cover more about that in the advanced sessions. Today we'll just be using a simple layout. And then we draw our graph. So I've got a choice for you here. I've actually, I think this might work best if we kind of talk through the code first of all. Probably best not to open a new script. If you've got two screens and can follow along and can write code at the same time, then please do. But if you're working off of one screen, you're probably better just to watch the presentation and use the script that I provided in the task files. So again, I provided you with the code. I'm going to provide, or we'll provide you with the code to be able to create the graph, but it's missing some information. And this is marked in the code with a double asterisk where there's something missing. So what you're going to need to do, and bear this in mind as we talk this through, that you're going to have to go through and fill in the missing data, the missing code, and in order to get this to work. And the inputs for this are going to be the node and edge lists that we created in the previous task. What you'll notice is if, oh, it's not in this one. If I show you the, go to the Git folder, in the task files and in data, there will be the graph creation backup data. If you didn't run or weren't able to get the previous task to run, then there is the edge list and node list data in there for you, just so that you can can carry on and do this task. Okay, so let's have a look. So building our network graph, we start with our imports. And in this, we are bringing in NetworkX, our main library that we're going to use for creating the network graph. And its little prefix that we can use is NX, is the standard convention for NetworkX in code. Then we import pandas as well, as we're going to use a bit of pandas in here. Most notably in our first read CSV. And here we're bringing in the data that we've just created. And here you start to see where we've got missing code that needs to be filled in. Obviously, I'm not going to talk about this because this is for you to work out exactly what the missing code is, but hopefully everything should be relative. You should be able to deduce what the missing code is without too much issue. So next, we said we need to initialize this empty graph object in NetworkX. So we use the nx.graph function to do that, and it just doesn't take any arguments. And here you need to give the variable that it's being assigned to. Then we do the node inputs and get the correct format for that. So as I mentioned, the node and edges, they are tuples. And in this instance, it's a tuple of the node ID and a dictionary of the attributes. So the node IDs are a list. They go in as we can see down here, it's named ID list. And then we create a data frame of the labels. And then they are converted into a dictionary as any attributes that need to accompany the nodes are entered as a dictionary in the tuple. And then here we're using going through, and this is list comprehension, doing a for loop and creating tuples for each node with an ID and a label. Then we go on to create the edge inputs. So this is going to be our source ID, a target ID, and then a dictionary of attributes. So the edge tuple takes the form of the source, the target, and a dictionary of attributes that accompany that particular edge. And so we create two lists, the source list and the target list. Then we get our weights, which are going to be the attribute that are going to accompany the source and targets for each edge. Convert that to a dictionary, and then again loop through and create the edge tuples where we have source list, target list, and the weight dictionary. Then once we've got our node and edge tuples, we need to add them to our graph object. And here we can just use the add nodes from and add edges from functions. And they will add, because we've got our list of tuples, they will all, if we put them into this function, they will then be added to our graph object, all of them together. So now that our graph object has its nodes and edges in it, we can determine how that's going to look. What we need to do is pass the graph object into a layout algorithm that works out how to position the nodes relative to each other and then join them up with the edges. And there's, as I mentioned, there's a number of different ways that this could be done. And they use various different layouts. Some of them are geometric, such as circular layouts or hierarchical layouts. And some of them are force-based layouts. So they work on based on physics engines that basically take proximity and gravity into account relative to the degree or some attribute of the node that it works out. And in this instance, we're going to use something called the Kamada-Kawai layout, which is one of these force-based layouts, which works nicely with this data. And then finally, we can draw our graph. And here we've got a few different arguments. We've got to pass in our graph object. We've got to pass the position in, the coordinate system that we want it to plot the graph based on. And then there's a few other arguments here that we've got the node size, so we can change that. And that could be determined by an attribute within the data, but here we're just using a fixed value. And adding labels to the plot and the font size for those labels. So your task now is to use the, so either you can go back through the slides and write your own script, or you can just use, I've got a file with that code in here, which is task2 graph creation student version.py. And you will need to make sure that your data is in the correct place. So if you've created your own data, that should be within the data folder that you've downloaded. That should now show there. If you're using the backup data that I provided, you'll need to move that from the backup folder into the data folder. So just up one level, and make sure that your working folder is still set correctly to the task folder. Okay, so I'm going to put you back into your breakout groups, into your peer support groups, and you can work your way through the task. I'll keep an eye, probably be about 15, 20 minutes on here, and then we'll just come back for a bit of a wrap up and go from there. Ooh, I'm back. Am I back?
Yeah, you're back. I thought that was me.
I'm back. Right. Okay. Sorry. My Zoom had a freak out there. If that happens, don't panic. Okay. Right now I'll put you into your breakout rooms, and hopefully it won't break. If anybody doesn't get the invite to their room, just let me know in the chat, and I can assign you.
Sean,
Yes. Hello.
hi. Sorry, I'm having a really embarrassing problem with the very first line of code getting the data to work. I just wondered if there's any chance you could help me, because otherwise I can't really run the rest.
No, absolutely. That's not a problem at all.
I think I'm just missing a piece of information.
Right. Okay. It might just be the. Do you want to just share your screen? Are you able to share your screen quickly?
Let me just find the right thing.
Yeah.
So I've spent the whole time fiddling around with it. I've actually got as far as this, which is better than I was before. But it says module pandas has no attribute CSV.
Right. Okay. So it's the function name that you've got there. So where you've got pd.csv. So the function is read_CSV. So it's pd.read.
Okay, great. Read_CSV.
Yeah, that's
I
it.
know. Perfect. Thank you. Sorry.
That should run now. Yeah.
What?
Okay, so what you need to do is set your working directory.
Okay.
So if you go up to the top right, where you can see a file location there, it's C:/users. And there's a little, right on the far top right corner, there's a little folder icon.
Yeah, because I just moved it all around, because basically I was just downloading everything and it did it as Excel. So then I was trying to change all this to Excel, and I've just re-downloaded it all, so I've got it as CSV, so I haven't changed that. That's great.
Okay.
Thank you so much.
No problem.
Thanks. I'm going to stop sharing now.
There we go. That's all good. I've got you there. Thank you.
Thanks.
Welcome back, everybody. That was great. I just kind of I popped in through the rooms, and it looked like I didn't like to interrupt, as everybody seemed to be doing extremely well. Any questions arising immediately out of that task? We're going to go through it in a moment, and I'll just kind of talk through what we were doing in each of the functions. Glenn, go for it.
Right, I just wanted to check, was the weight of the edge meant to show in the plot anywhere? I couldn't see that it was.
No, it wasn't. The edge weights weren't turned on in that one. No.
Okay, thanks.
No, well spotted. Yes. Okay. What I'll do is I'll share my screen, and we'll just run through the task very quickly there. So, right. So, as everybody worked out, actually, one thing I did see and hear, people picking up on the use of the little eraser up here in Spider to clear your environment. It's a good little Spider tip, that one. Okay, so what we start with is doing our imports, and it reads in the node list, but then we need to read in our edge list as well. And so we've got to enter this string with the data and then edge list.csv. It'll be a common theme across all the sessions that you do with me. I don't use Excel files. It's always CSVs and reading in this fashion. I much prefer CSVs just because we don't have to bother with any nasty formatting or funny things that might be hidden in the file itself that can mess up the read. Then we need to initialize our graph object, and that's assigned to the variable g. So hopefully that was a nice easy one. We'll just pop g there. Now we're going through and we're making our node tuples. And so the first thing we've got to do is read in our get our ID list. So I'm just going to run this first section here and up to initializing the graph object. And from the nodes, as you're all rightly doing, great to see, go in, look at your data. Okay, what's our column name that we need? We need ID, and it's capital I, capital D in a string. So we'll do ID in there, and we're converting that column into a list. And then we're going to get our labels as well. And so extracting them from the nodes data frame and turning the labels into a data frame in their own right. And then from that labels data frame, we can convert that directly to a dictionary object. And so that is that we just need to convert labels to dictionary. And then we can have the node tuples created in the loop for all of our nodes. And so the output that we get for them, and we can see this tuple that we've got the ID number and then the label as a dictionary object, with the key being label and the value then given as the label name. Okay, moving on to the edges, we get edges, and we need to say where our source data is coming from. That's coming from the column source. Capital S, it's always good to check your column names. So we've got that there. And then we need to get our weights. And again, the edges, we're using the edge data, and that is coming from, and I need to check, is it got a capital W on weight. Okay, and then we're going to convert that to a dictionary again. So that is weights with a small w. Okay, and then just one more to change here, that we've got our edge tuples. And so here we're using, we've got a source list and our weight dictionary, but we also need our target list. And then we can run that. And oh, that's the target list. I want my edge tuples. There we are. And so this time we have the source, the target, and then the weight in the dictionary as the key being weight, and then the integer value as of the weight as the value. Okay, finally, we're going to add our nodes and edge, or almost finally add our nodes and edges. So we've got our node tuples, and we've got our edge tuples. And we can run that. And they've now been added to our graph object. And then we just need to add the, graph object to the layout and run that. And that gives us our position. And these are coordinates that it will use to place each of the nodes. And they're just on a Cartesian coordinates, XY coordinate system. And then for the plot, we give our graph object as the first argument. That's always the first argument. And then we require the position keyword, and that's the one that we've just created, our pos variable. And we can do that, and our plot is plotted. There. In the advanced sessions, we'll be covering all the some more advanced plotting packages where we can get some interactivity in our plots, which is always good fun. I think we'll see how much time I get. We'll look at perhaps hollow views and Plotly Cytoscape for creating those, as well as a little look at Gephi as well, as it does still produce some very nice visualizations. Okay, just coming back. So we got a couple of bits in the chat. Okay, hopefully I've gone through and shown the correct outputs. Matt, are there any particular outputs that you'd like to see that I haven't shown, or is that all okay? No, okay. Lee, it might be that your plot is showing in the plots window. That's quite a common one now, as plots don't show as separate windows in Spider anymore, which is a bit annoying, but one of those things.
Yeah, sure. I think I'm using PyCharm, and normally I should, like, if I use matplotlib, I need to use like plt.show
Yeah.
to have the plot. But in this example, is there any code I should be adding to make the plot show?
Yeah, it is try
plt.
well, it will be
I did a
it'll-
plot.show and it came up.
Oh,
yeah,
cool.
it'll
So I
be
need to
plot.show.
import the matplotlib.
Yeah, it might be a dependency, but I'd import it explicitly anyway.
Right, cheers.
Okay. Katie, if you want to put your code, send it to me in Slack and I can have a little look at that. Shilpa, can't seem to populate your edge tuples. Do make sure that you put the target list in there. Again, yeah, if you want to send me your code on Slack, I can have a little look and get back to you more specifically about that.
Thank you.
Okay, great. So well done, everybody. You know, like most people getting there and a few little niggles, but always is with coding, debugging. There's it will always, even if it's supposed to be easy, there will still be instances where you go, why isn't that working? And debugging becomes a way of life. Nothing wrong with that. Just to mention, I'm just going to share my screen quickly and show you. So in here, I've given the link to the NetworkX documentation. And if I just go into that, so it's got pretty good documentation in here for NetworkX. And it goes through everything, all the different, get everything from graph types. So where we're talking about different digraphs that haven't gone into multi-graphs, they're not, it's not hugely common. You get parallel edges added in there. But normally with a standard digraph, you essentially get that anyway. Multi-graphs are just a bit of a, that you get parallel edges added in. It's a bit of a distinction with no distinction, so I won't linger on that. We get it also then, and we'll cover this next time in the first advanced session. We'll look at the whole the wide range of actual analysis metrics and go through the most useful ones, particularly around looking at centrality in the graph and kind of understanding the graph structure and what we can be comparing over time. But yeah, these really useful documentation if you did want to have a look at this a bit more on your own. Just to note that there's down at the bottom of the drawing bit here, these are the different layout algorithms that we get within a standard within NetworkX, and these are kind of, you get okay layouts with NetworkX, but in the second advanced session we'll be looking at some even better visualization techniques and looking at how we use NetworkX alongside these other libraries Network X to do our analysis, and then we do our visualization with a different library. So yeah, just to reiterate that, yeah, so we'll be looking at different types of graph metrics and their interpretation, how graph visualizations work, graph algorithms and custom layouts, and interactive graphs with Plotly and HoloViews. So I'm doing a project around the use of network analysis for large-scale operational modeling for healthcare, and check out project-nom.com for a little bit more information about that, although I haven't updated the website in a little while, but there's still some bits of information about the work that I'm doing there. Or do get in touch if you'd like to know a bit more about network analysis. And I'm going to pause there and ask if there's any final questions. Okay, yeah. How do you decide the weight of an edge? So it's all about the amount of activity. It's the amount of times that that edge is used. And that's what we do when we're counting up in our adjacency matrix. So that where we see those different numbers, that's the number of times that we see a patient moving between two services. And that is our weight that we use. And yeah, depending on what you have, what your entities are and what the meaning of the link is, that is what will determine the weight. Anything else? Okay, practical change with network analysis. There are a raft of examples online, and the benefits to potential stakeholders. Yeah, I mean, with a quick Google uses of network analysis, you'll be able to find tons of examples, particularly around logistics is a massive use area. There's some good examples around town movements and looking at town planning. This is particularly being done by a group at the Turing Institute, who are doing something similar to myself, where they're working at looking at change over time within town transport planning and traffic planning in towns and cities, and being able to plot how people are moving around and looking at how that changes, bringing time in as a component to the analysis. Yeah, lots of examples online. But yeah, in terms of it being used in healthcare, very, very, very few examples of it. And it's kind of one of those which is just starting to be used within healthcare settings. Yeah, I would recommend have a look at the Devon and Cornwall Police presentation from the HSMA 3 showcase. It's a really nice example of how network analysis can be used in practice as well. Okay, anything else? Otherwise, you can get an extra 10 minutes on lunch, which I'm sure all benefit on, as you've got machine learning this afternoon, and I know it's going to be a great session. Dan's introduction to machine learning is a brilliant one, and it's a fascinating topic area. So I think you could all do with a good reset of the brain and get ready for this afternoon session. Thank you for joining, and yeah, you can always get hold of me on Slack if you've got any questions or want to throw project ideas around, see if something's practicable to do for your project pitches. Always happy to have a chat and help out. Thank you, everybody. Take care. All the best. Take care. Bye.
Thanks.